So colligative properties with strong electrolytes. The strong electrolytes separate into ions, so there are more particles. Like sodium chloride has 2 ions per formula unit, we would expect there to be twice as many particles. It's not quite that simple. So the Van 't Hoff factor gives us the ratio of moles of particles to the moles of formula units dissolved. And so it's sort of a correction factor. The reason that it doesn't work out exactly right is because some ions effectively pair up in solution, and so they don't really act like individual particles. They go around holding hands, and so they're like acting like one particle. So we see ion pairing. The chlorides dissolve, the sodiums dissolve, but they're still hanging out together. So the expected values would be the number of ions in a formula unit. So FeCl3, there's 1 iron and 3 chlorides. We would expect there to be a factor of 4. It's actually 3.4. So they're always going to be less than we expect. So the correction is for an electrolyte, you take the Van 't Hoff factor and you multiply it by the osmotic pressure, the freezing point elevation, freezing point depression or boiling point elevation. So same equations, but you just throw an I in front of them. Calculate the freezing point of an aqueous 0.1 molal iron 3 chloride solution using a Van 't Hoff factor of 3.2. The Van 't Hoff factor would be given to you. If it were not, then you would assume ideal behavior and it would multiply by 4, because theoretically there's 4 moles of particles per 1 mole of FeCl3. So the freezing point depression is going to equal the Van 't Hoff factor times the molality times Kf. So they gave us the Van 't Hoff factor to use, and the molality is 0.10, and the freezing point depression constant is 1.86 degrees Celsius per molal, because I happen to remember it, that's all. So 3.2 times 0.1 times 1.86. 0.5952. This is aqueous, and so the actual freezing point is going to be 0 minus that, negative 0.5, well, negative 0.60 actually. Any questions? I got the 1.86 from my head. That's not a good answer, is it? This is the freezing point depression factor, Kf, for water. You'd go look it up in a table. Yeah. Any other questions? Mm-hmm.
So the formulas will be provided, but will those values, 1.86?
Yes, I would give you freezing point depression constants. If you need the Van 't Hoff factor, it would be given to you. Those aren't things to memorize. Strong electrolytes have a bigger effect on vapor pressure as well. And here we have to account for the dissociation of the solute when we're talking about the mole fraction. So if we're trying to calculate vapor pressure of a solution with an ionic solute in it. So here we're given, we've got 0.115 moles of water, and here's the vapor pressure of the solution, here's the vapor pressure of pure water. They're asking how many moles of sodium chloride. Well, the vapor pressure of the solution is equal to the mole fraction of the solvent, which is water, times the vapor pressure of the pure solvent. So here we're given the vapor pressures, and we can use those to calculate the mole fraction of water. They're saying the vapor pressure of the solution is 25.7 torr. The vapor pressure for pure water is 31.8 torr. Zero point 808. So that's the mole fraction of water. That equals moles of water divided by moles of water plus moles of ions. Well, they told us moles of water. So we're going to do some cross multiplying here. So I'm going to take the 0.808 times this denominator. So I'm going to get 0.808 times the moles of water plus 0.808 times the moles of ions. And that's going to equal the moles of water. So we end up with 0.808 times moles of ions being equal to 0.02208. Divide both sides by 0.808. We end up with 0.0273 moles of ions, moles of particles, right? It wants the moles of sodium chloride. Sodium chloride, we're going to ignore Van 't Hoff factors. Sodium chloride dissolves, it forms two ions, right? So if we want moles of sodium chloride, we get 1 mole of sodium chloride for every 2 moles of ions. So we have to divide by 2. .0137 moles of sodium chloride. It's another critical thinking problem. Colligative properties are important in medicine. The osmotic pressure of a solution, especially as an intravenous fluid, is really important because you don't want fluids introduced into the bloodstream to cause osmosis within the body, basically. So a hyperosmotic or hypertonic solution has a greater osmotic pressure than body fluids, and so will draw water out of the cells. So that's going to happen here. Hyperosmotic solution causes red blood cells to shrivel up because the solution outside the cell is more concentrated, and so it pulls water out of the cells. Normal red blood cells look like this. You want the solution being administered to be isoosmotic or isosmotic, isotonic, so that it has the same concentration of particles as inside the cells, and so the water flow across the membranes does not get disrupted. If you have hypoosmotic, below pressure, so like pure water or something that's very dilute, that's going to cause water to flow into the cells. It's going to cause the red blood cells to swell up and they can eventually burst. Not good. I kind of said all of this. Isotonic saline is 0.9 grams sodium chloride per 100 milliliters, or 0.9% mass to volume. And that is pretty much what all IV fluids are based on, is that 0.9% sodium chloride solution, mass to volume. In medicine, they often use a percent mass to volume, or a straight mass of solute per volume of solution, because it's easier. If you want to give someone 0.9 grams of sodium chloride, you can just measure 100 milliliters of the solution. You don't really have to do much calculating, and so that's a very common unit.